Hi, so today I wanted to do a quick video to kick off Unit 2 Standard 1, which our standard is I can solve systems of equations. And the learning target that we'll be tackling in this lesson is I can solve systems of equations exactly and approximately, e.g. graphically, focusing on pairs of linear equations in two variables. So first off, we want to do a quick intro. So what exactly is a system of linear equations? So first off, we all know what a linear equation in two variables is. We've done this before. We have y is equal to, say, 2x minus 4. So, and we could graph this equation, and a reminder that the y-intercept would be -4. So we can plot that right here. Our slope is 2, which would mean that for each 1 unit we go right, we would go up 2. And then once we have 2 points, we just connect them. It's going to look something like that. That's just an approximate graph, but it will do the job for now. So on this line, there's an infinite number of solutions to this equation. And that's because any point on this line will satisfy this equation, meaning that if we plug the x and the y values from the point into the equation, we will get a true statement. So let's take a look at some points that satisfy this equation. So let's try 0, -4. So that means that if we plug 0 in for x and -4 in for y, we should get a true statement. So let's see. We would get -4 is equal to 2 times 0 minus 4. Then we get -4 is equal to -4, which is a true statement. So that makes us happy, right? So now let's just do another example. Let's do the point, let's say 1, -2. So if we do 1, -2, we have -2 is equal to 2 times 1 minus 4. If we do this subtraction, we get -2 is equal to -2, which again makes us happy. So that's just two examples, but there's an infinite number of these coordinates that will satisfy this equation. So now, suppose that instead of just one linear equation in two variables, we have two linear equations in two variables. So let's do y is equal to 1/2 x plus 3. And let's just say y is equal to -3x plus 8. So if we want to solve this equation graphically, that means we want to find the coordinate point that both of these lines share. Because as we went over earlier, each of these individual lines has an infinite number of solutions. However, combined, these lines may only share one solution. So we want to find that out. So let's graph this one first, although it doesn't matter which one we graph first. So y-intercept is 3, slope is 1/2, so that means for every 2 units we go right, we go up 1. And our line's going to look something like this. Now let's graph our second line. So y-intercept is 8. We'll put an 8 up here. Slope is -3, meaning for each 3 units we go down, we go right 1. And we'll get a line that looks something like this. And so you see that the only point that these two lines have in common is this point. It's right where they cross, which is approximately something like 2, 4 maybe. And here we're seeing one of the shortcomings of solving systems of equations graphically is often you'll only get an approximate answer because we don't know exactly where those points cross without either graphing software or really good rulers and graph paper. So now that we know that the solution to a system of equations is the point at which the two lines cross, let's do a couple examples. So I'm just going to get this whiteboard over here. And first off, let's do y is equal to 2x plus 2. And how about y is equal to negative 1/2 x minus 4. So let's graph this one first. We have our y-intercept is 2, our slope is 2, so we're going to have these 2 points. Then we're just going to draw our line on the grid like this. So that's what our first equation is going to look like. Our second equation, we have a y-intercept of negative 4, and then we have a slope of negative 1/2, meaning that for every 2 units we go right, we go down 1. And if we graph this equation, we're going to get a line that looks something like this. And we see that the lines cross at one point. So this point right here is the solution to our equation. So let's find out what it is. We have on the x-axis, we're going back 1, back 2, back about 2 1/4, I would say. So x is equal to negative 2.25, which we could also write as negative 9/4 if we want to use fractions. And our y-coordinate, we're going down 1, 2, about 2 3/4. So our y-coordinate will be about negative 2.75, which is also equal to negative 11/4. So you see that's a pretty good solution to this equation. And we could either write our solution like this, or we could write it as a coordinate pair, where we write the x value, negative 2.25 and negative 2.75. And then we'll celebrate our answer by putting a nice box around it. And so that's one example of solving a system of equations graphically. So now on an assignment or on a test, if you're asked to solve a system of equations graphically, you know what to do. And I expect an answer kind of like this. So now let's do one more example. Let's say y is equal to 3x minus 2, and y is equal to 5/4 x. So y is equal to 3x minus 2. We'll plot our y-intercept. It's negative 2. Our slope is positive 3. So our graph is going to look something like this. Again, not perfect, but pretty good. And our second graph, the y-intercept is 0. And we would have y is equal to 5/4 x, which means for every 4 units we go right, we're going to go up 5. And we're going to get a line that looks something like this. So now we'll see where the lines intersect right here, which is just about, let's say, our x value is about 0.9, I would say. It's pretty close to 1. And our y value is about 0.85, let's say. And we could, again, put these into fraction forms if we want. We could say this is equal to 9/10. We could say that 0.85 is equal to 17/20. And if we wanted to write our answer as a coordinate pair, we could write 9/10, 17/20. So that is how you solve a system of equations graphically. Going forwards, we will, in the next video, we'll discuss what happens if lines cross more than once, or what happens if the lines don't cross at all. And then beyond that, we'll go over how to solve systems of equations exactly using algebraic techniques rather than graphs. Yeah, so that's it.